Okay, these questions are not necessarily in the same order you got them. They're all shuffled. All right, number one, electron moves from a higher energy level to a lower energy level. So there's your nucleus. Energy level one, energy level two, energy level three, and so on. When an electron moves from a higher energy state to a lower one, right, that's going to produce um, light or a photon with a certain frequency. That might be right there. Okay, something like this here might be, well, that's going to be in the UV range, so that won't register in visible light, but that might be way out here. So higher energy state to lower energy state is releasing energy. Number two, by the way, if the question has lower to higher energy, then that would be absorbing energy. Okay, so an electron in a lower energy can move to a higher energy if it absorbed energy. Number two, electronegativity trends up and to the right. Fluorine has the highest electronegativity. This question is asking what is the lowest electronegativity. So the answer is going to be down and to the left. There we go. A is your answer. How does calcium obey the octet rule? Calcium is in, let me just show you where it is. Calcium is over here. It's an alkaline earth metal. It's group 2. So those elements have 2 valence electrons. They're going to lose those 2 valence electrons, right, to have the electron configuration of the previous noble gas, which is not on here, but that would be neon. All right, so how does it obey the octet rule? In other words, how does it achieve the electron configuration of a noble gas? It's going to give up 2 electrons. Well, let me read these other choices. Well, it's not A, it's not C. Oh, okay, answer is B. All right, which of these atoms are least likely to form a compound? In other words, an ionic bond or a covalent bond. Your noble gases are not going to form compounds generally, especially the ones higher up, neon, helium, and argon. And we'll see, we have examples where some of the larger noble gases can form compounds. All right, number 5. Let me change up my colors. The diagram shows which 3 elements would have the most similar, would most similarly react, similar properties. So you're looking for the elements with the same number of valence electrons. That would be A. So that might be like oxygen and sulfur and selenium, group 16. Okay, even the elements in the same group, can be very different, but this is even worse, and these are all going to be much, much more different. So you're always picking the best answer, and so we've been learning fundamentally when atoms have the same number of valence electrons, they're going to behave similarly. Okay, although that's kind of subjective. All right, number 6. All right, smallest radius. Which of these atoms are the smallest? All right, so as you go down the periodic table, atoms are going to have more and more energy levels, so they're going to get bigger. 1, 2, 3, 4. 1, 2, 3. Okay, so they're going to get bigger as you go down. So the smallest is going to be up here. So let's see if we have an easy answer. All right, we don't, because they're all right here next to each other on the in the second period. Okay, so as you go across to the right, atoms get smaller. So in the second period, they all have 2 energy levels, but as you go to the right, they get smaller and smaller because of the increased nuclear charge. Increased nuclear charge. So fluorine is going to be, wait, are these the choice? Yeah, fluorine is going to be smaller, and neon will be smaller than that. All right, number 7. What do N, P, and AS have in common? All right, they all have 5 valence electrons. Is that a choice? Yep. D is not correct because they all have different number of electrons. Nitrogen has 7, phosphorus has 15, and arsenic's 33. Are they all nonmetals? No, arsenic is a metalloid. And all right, C's the answer. High melting points conducts electricity. So we did a lab on this. We put ionic and covalent compounds on that tin lid and heated it up, and it's the ionic compounds that did not melt. It's the ionic compounds that lit up our most accurate measuring device, the light bulb, with connected to that battery. So B is the answer to that one. Number 9. Scientists discovered a star. A star concluded is mostly made of hydrogen and helium. What? Oh man, I got the wrong image. All right. I thought that said helium. It says potassium. Anyway, all elements have a unique, what are these called? Atomic emission spectra. Right, and that's because they all have a unique number of electron and proton combination, making those electron transitions unique. So that's going to produce a light unique to helium and potassium and hydrogen. So each element has a unique. Okay, A sounds good. Measuring how long it takes. Nope. Multiple elements share the same. Oh, that's the opposite of what we're trying to teach you. Density stars can be. Guess you could do that. I don't know how you would do that. Okay. 10. Chapter 5. We spent a whole chapter on quantum numbers, right? First quantum, this is a Schrodinger's equation. We don't have to know that. That's too complex. But the solutions to this equation tells us the principal energy level, tells us the angular momentum or the shape of the orbital, tells us the magnetic quantum number or the direction, the orientations of those orbitals, and tells us the spin of the electron. So all of these describe electrons. Number 11, net charge on calcium fluoride. All right, calcium, it's at the second column of the periodic table. We know it's going to lose 2 electrons to become a 2 positive cation. Fluorine is a halogen, so at a 7 valence electron, it's going to want to gain 1. It's going to want to gain 1 to become a 1 negative anion. All right, when these form a bond, you're going to get calcium fluoride. Looks like that. So the 2 negatives here, because there's 2 of them now, and the 2 positives there are going to cancel out. So ionic compounds are neutral. That's the premise behind the formula unit, right? So ions do have different charges, but when they form a compound, that compound is neutral. Doesn't have a net charge. Right, number 12, you didn't need your formula sheet because the visuals right here. All right, so the longer the wavelength, which is, maybe I should use red. The longer the wavelength, right? They're all moving at the same speed, right? The speed of light. Okay, so they're all moving at the same speed. So the longer waves, a few of them are going to pass through. So the longer or the greater the wavelength, the lower the frequency. So we gave that to you also on the formula sheet. If you wanted to use c is the speed of light, and this is wavelength, and that's frequency. So if one goes up, the other one has to go down in order to make this true. That's a constant. All right, inversely, there it is. A. Let me just check the other ones. Frequency is wavelength divided by. All right, so if you rearrange that, it's these two things are switched. So B is not correct. Wavelength is determined by dividing frequency. Frequency divided frequency. Hold on. Wavelength is that. If we rearrange it, is determined by frequency divided by. No, that's also flipped around. That's backwards. All right, they are directly. No, they're not proportional. Okay, answer is A. Third principal energy level. So right, n equals 1. You only have your s orbitals. Just s. Second principal energy levels, you have your s, and then you have your 3 p's. And then in your third principal energy level, you have your s, you have your 3 p's, and then you have your 5 d's. So SP's and D's. All right. Mendeleev, how do you organize his periodic table? He ordered them by mass. Choose all that apply. All right. So there were a couple problems where he had loads check boxes. So you had to, there you go. Mass and similar properties. Okay. All right. This is how it should be organized, atomic number, but he didn't know. He didn't know that there were subatomic particles. At the time, they weren't discovered, which I believe is an answer to another problem. All right, what's the bond angle around carbon dioxide? So we've done this at least couple times in our class, and there's a video on Canvas too. So if you draw the Lewis structure for carbon dioxide, there it is. So the central carbon has 2 electron domains. So that angle is 180 degrees. It's linear. It's a linear molecule. All right, number 16, the Lewis dot structure for magnesium fluoride. All right, let me just make another section here. All right, magnesium is a group 2 element, so it's going to form a 2 positive cation. Fluorine is, I feel like we just did something like this. All right, fluorine is a halogen, so it's a group 17. It's going to gain an electron. All right, we're going to need to crisscross these numbers to get the formula unit, and so it's going to be MgF2. All right, so we're going to need 1 magnesium, 2 valence electrons, and 2 fluorines. I could have drawn this a little better. All right, that's going to go there. That's going to go there. This ionic bond is a metal and a non-metal, so we know that's an ionic bond, so that we're going to transfer these electrons. All right, magnesium losing its 2 electrons is going to be a 2 positive cation, and then fluorine each are going to gain an electron, and C is the answer. Geometry of iodine trichloride. This is, I believe, also right in our notes. Not that that makes it easy. There's a lot of notes we take in our class. All right, these are all halogens, so they're all 7 valence electrons. So we need to draw the Lewis dot structure, okay, to figure out geometries. All right, there's 1 plus 3 there, so it's 4. Okay, 7 times 4 is 28. All right, let's put iodine in the center. Try to draw that I again. How many chlorines? We got 3 chlorines. All right, we need a bonding pair between the terminal atoms and the central atoms, so that's going to use up 6 of our electrons. We're down to 22. We're going to put 6 on each of the terminal atoms. That'll give them an octet. All right, so the chlorines are all good. All right, we used 18 electrons in that process, so we're down to 4. any remaining electrons will go on the central atom. So something like that. All right. So we have 1, 2, 3, 4, 5 electron domains. That's why I have this image here. All right, and 2 of them are lone pairs. So it's going to be T-shaped. If you remember, all right, you got to pull out the ones on the top or bottom. If you recall, I believe it was Ty that recognized, hey, you don't want to. I'm sorry, what did I just say? You don't want to remove that one. You want to remove one of the side ones. Oh man, I'm a little distracted. Yeah, you want to remove one of the side terminal atoms, because by doing that, now it only has to be next to 2 other uh, electron regions at a 90-degree angle. Right? Whereas if you would have taken this one out, then it had to be next to 3. All right, so you're going to pull out a side one, and so that's going to lead to a seesaw geometry. But then you pull out another side one. Okay, so there's the first one we pulled away, and there's the second one. You're going to get this T shape. All right, answer is T shape. All right, number 18. Carbon tetrafluoride. So 4 valence electrons plus 7 times 4. Too much math. 28 plus 4 is 32. Let's put carbon in the center. All right, 2, 4, 6, 8. Bonding pairs. 8. 32 minus 8 is 24. All right, fluorines. Get them each 6 more valence electrons. Whew, that's 24. We use it all up. 6 times 4 is 24. All right, so central carbon has 1, 2, 3, 4 electron regions. That's tetrahedral. Answer is B. Tetrahedral is 109.5. Oh, more low structures. Okay. SF4, sulfur. It's got 6 valence electrons plus fluorine has 7 times 4, which 24, no, 28 plus 6 is 34. Okay, 34. We write that down. All right, let's put sulfur in the center. Surround that with 4 fluorines. All right, they all need a bonding pair. So that's 2, 4, 6, 8. 26 we're left with. All right, let's get the terminal atoms, the octet. That means we add 6 more electrons to each of the fluorines because they already have 2. That'll get them the octet. All right, so that's going to give. How'd you do, Ryan? You're live. Yeah, how'd you do? All right, where were we? 26, I see on the board. Oh, right, I just had a student stop in and say hello. So 20, oh, we just added 6 electrons to each fluorine. That is 24. 6 times 4 is 24. We have 2 left. Where do they go? They go on the central atom. All right, why do we do all this? To pick the right answer, C. Okay, number 20. What's wrong with this diagram? There's a lot of, everything's wrong. All right, those 2 need to go there. That's Aufbau's principle is violating. All right, this is violating Hund's rule because each electron needs to get their own orbital if they're in the same energy. And then that's violating Pauli's rule. So they're all being violated. Molecule has a slightly positive charge and a slightly negative charge. It's like water, right? Water, H2O. One side is slightly positive. One side is slightly negative because of the differences in electronegativity. We call water and other molecules like that polar. They have a significant difference in electronegativity. All right. Which molecule does Vesper predict to have a square planar geometry? All right, well, that means the central atom um, needs to have 4 around it. So, like, we can eliminate B, we can eliminate C. So they wouldn't give you squares because you would need to have 4 surrounding a central atom. We just did this one, so we know that's not the answer because we did we just did that. And in order for us to get a square planar, we need to get a octahedral. We need to get 6 bonding regions. In other words, octahedral electron geometry. So A is going to be the answer. Let's do this because you may not have gotten the same order, right? All right, xenon has 8 valence electrons. Fluorine has 7. There's 4 fluorines. That's 28 plus 8 is 36. All right, 36. All right, let's put xenon in the middle, connect it to 4 fluorines. 2, 4, 6, 8. We've used up 8 electrons, so we are down to 28. All right, let's get fluorines, their octet. All right, so another 24 right there. So we're down to 4. All right, so there is our 1, 2, 3, 4, 5, 6 regions of electrons. 2 of them are lone pairs. All right, this is 0 lone pairs. This is 1 lone pair. This is 2 lone pairs. So the answer is square planar. Answer is A. Okay. Manganese, it's right here. 25. 25 valence electrons. All right, but we got to remove 2. Right, so manganese is going to have a neutral manganese is going to have an electron configuration of argon plus the 4s2. 1, 2, 3, 4, 5 plus the 3d5. All right, we got to remove 2. They're going to come out from the s orbitals. Remember that. Transition metals will lose their s electrons before their d's. So there it is. Formula unit. All right, sodium is a group 1. So it's going to lose that 1 valence electron. It's going to become a 1 positive cation. Oxygen, oxide is oxygen. So 1, 2, 3, 4, 5, 6. It's going to want to gain 2 electrons, and therefore the oxide ion is going to have a 2 negative charge. All right, crisscross. There's your answer. Answer is B. Which of the following diatomic elements does not contain a single bond? Hydrogen definitely does, because right there, fluorine, chlorine, they're both halogens, so they're going to also. Let's just do one of them. Right, so they're going to have 1 bonding pair. That'll give them 8. You can count them up. There's 2, there's 4, there's 6, and there's 8. So there's no need for it to create another bond. All right, oxygen is going to be the answer. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right, so you share. That's a bonding pair. That's going to get them both 8. I'm sorry, 7. Share another one now. They'll get to 8. Right, 2, 4, 6, 8. right? So oxygen is going to have a double bond. No single bonds. All right, the image is not above. I just copied and pasted below. All right, what was a challenge he faced? He ordered them by mass, which worked out for a lot of them, but he would have had to know that they were protons, um, but they weren't discovered. All right, electrons exist in these orbitals. Let me just draw one. All right, we can give that electron energy, and it can go into the 2s orbital, and then it can go into the 2p's, and then you can go to 3s, and then go higher and higher and higher. Eventually, that electron can leave the atom. We call that ionization, and the energy it takes to remove an electron is called ionization energy. That trend increases up and to the right. It gets harder to remove because those electrons get closer to the nucleus, which is where the attraction is coming from. So up and to the right, neon is the answer. It's going to be very, very hard to remove an electron from neon compared to those other choices. In fact, the only other one would be helium, which is not up there. Would have a higher electronegativity. I'm sorry, ionization energy. All right, what's a metalloid? It's going to be one of these. So silicon. What? Oh, choose all that apply. Okay. There's another checkbox question. All right, here we go. Not conduct electricity. So we're looking for covalent bonds. This has a metal. That's a nonmetal. That's ionic. That's going to conduct electricity. Metal, nonmetal, ionic. That's going to conduct electricity. All right, so these are your correct answers. They don't have any metals. They're covalent bonds, covalent compounds. We actually put this is glucose. We actually put that up one of our substances on the tin. The other two were also substances on our tin lid during our lab. Transition metals are elements that have their final electrons in the D block. So this is the D block. This might be a checkbox question too. Right, silver, right there. Chromium, yep, right there. Nope, aluminum is there. It's not a transition metal. Calcium doesn't have aluminum nor calcium have electrons in the D orbital. All right, which of the following are most likely to form hydrogen bonds? Hydrogen bonds, again, is intermolecular attractions between hydrogen and either fluorine, oxygen, or nitrogen. Okay, so that one doesn't even have hydrogen, and neither does that. So that C is going to be the answer. So classic example over here to the right. These are hydrogen bonds. It's the oxygen. There's your H and O right there, interacting with another H and O. Okay. All right. Now, if you know what language that is and how to read that, why don't you let me know? I don't want to even take a guess. But I bet you that can be translated into hydrogen bonds because I love this image. I couldn't really find one with an English label, but I bet you that's what it means. Right, there's your H and F interacting with another H and F, so these are known as hydrogen bonds. All right, a couple more to go. Some possible note, the momentum and the position, or the velocity and the position. Excuse me, that's a Heisenberg. What is true about another Lewis structure? 5 plus 6 times 2 plus 1. get that one negative charge, right? So let's see, that's 6 times 3 is 18. All right, nitrogen goes in the center. It's less electronegative. Let's put the two oxygens around it, make a bonding pair between the two. That's going to use up 4 of our electrons. We're down to 14. 2, 4, 6. 2, 4, 6. That's 12. We have 2 left. Put them on the nitrogen. All right. Nitrogen needs more electrons. It only has 2, 4, 6. It needs an octet, or it really wants one. So when we use up all our electrons and we still need more for the central atom, we can take a lone pair and make a bonding pair. Right. So there's nothing wrong. So all of this is one negative charge. So that little structure is good. A. According to Vesper, another. All right, little structure. N is number 5. H, hydrogen has 1 valence electrons, and there's 3 of them. That's 8. Put nitrogen in the center. Put the 3 hydrogens around it. 2, 4, 6, 8. All right, we have 1, 2, 3, 4 electron regions, which is why I pasted this image next to this problem. We have 1 lone pair, so the answer is going to be a pyramid with a triangular base. Trigonal pyramidal. Let's see. Done. Last one.